My name is Héctor, Marín, and I'm just going to give like following talk to Will and Guy. So basically, I'm just going to focus on resistive distortions, varying acoustic oscillations, and at the end, higher order statistics. So I'm just going to start talking about how we estimate or how we measure the power spectrum from surveys and which is the effect on terms of selection function, and afterwards just going to speak a little bit about the effects that these two things have on RSD video, and the final part of the talk I'm just going to move to the bispectrum signal. So probably you've seen this. I mean, basically our sampling field is just measuring galaxy positions, then we convert these galaxy positions into density, and from density we just map it towards these over density parameters. This in configuration space, and we can Fourier transform it to Fourier space, and just we can either work with this or the other. So from these two fields, we can either define the two-point correlation functions, which is just this thing here, or the power spectrum, which is exactly the same thing, but instead of in configuration space, in real space. So usually our observables is not the delta field itself, but the two-point correlation functions, and eventually the 3 or 4. So our recipe to measure like features from the universe can be estimate, BAO, or wherever is just can be given by these three things, which is measuring the power spectrum, monopole, quadrupole, wherever, then taking into account the selection function, which I'm just going to describe a little bit. And then the second part is about the modeling in terms of how you model your diameter power spectral galaxy. You put resistive space distortions into it, how to account for the galaxy model, covariance. So most of these things have been described along the talks. I'm just going to focus on these two things. So real-life problems of cosmologies, we measure P of k from resistive space, just listed here in a bit. So basically, it's a non-uniform distribution of galaxies. Because the distribution of galaxies is not uniform, we cannot just directly measure power spectrum as if we had a periodic box. There are other things like how the photometric conditions vary across the survey or the fiber collisions that I'm not going to go into details of it. So how we deal with this thing, with the first thing, is through this estimator, through the FKP estimator. So these FKP estimators is defined this way. We have basically this is the main signal we measure from the survey, our density of galaxies as a function of position, and then we have a way that it can account for many things. It can account for this how the density field varies across the survey, how we account for fiber collisions and other stuff. And we have as well what is called the random catalog. So the random catalog, it has to have the same features of the data, but without any clustering feature. And basically this is like our reference point to measure this. So we are going to measure this with response to this. And the excess of things we measure is the real clustering signal. So the way we do this thing is to construct our power spectrum estimator into this way. So we define this function, which is going to act as our delta field, as if we were putting this, but instead of this, we are putting the whole thing. And then we can define the power spectrum multiples into this way. So this is basically is sort of a Fourier transform of this delta, of these F2 fields, but with some thing here, which is going to describe the line of sight dependence. So I'm just put the same equation here. So the argument of this function is what it really complicated the thing. So in principle, this is the kind of RH, and it's like the line of sight here. So we will have our observer here, and we are observing a bunch of galaxies here. This RH vector would be like the center of the curve. So for the monopole, if we want to measure the monopole, it turns out that this function, this Lagrange polynomial of order 0, is just 1. So it doesn't matter the argument, because it's 1 always. So in this case, we can rewrite this expression as this. So we just substitute this by 1. And then if you look at it, you will see that these two integrals are separable. So we don't have this piece anymore, and these two integrals actually can be like written, reordered as a Fourier transform. So you see that this is actually the Fourier transform of this component. So then it's very easy. because actually the monopole power spectrum is just the Fourier transform of this thing. So we just have to measure F and just Fourier transform using a FFT, a fast Fourier transform algorithm like FFTW, and just taking the angular average, then we will get the monopole. However, things get more complicated with quadrupole, because we have this thing here, which is not 1 anymore, and actually if we expand this thing in terms of the actual polynomial, we will have like a term which is crossing R1 and R2, and makes this separation of the intervals impossible. So what we do here is what Will was describing is this approximation where we substitute the line of sight to the middle of the pair by the line of sight choosing one of the objects. So this is what is called this local plane parallel approximation. And we're just substituting the argument of RH by R1. And then you see here that if we reorder things here, now we have like Fourier transform and something which is not exactly Fourier transform, but actually we can write it as several Fourier transforms. So the thing here is that we have been able to rewrite the quadrupole as a set of Fourier transforms, which really simplifies our life because it makes the calculations much more simple. So the next thing is how we deal with the survey geometry function. So the estimators I've just described here measure this thing, but this is not actually the underlying power spectrum, it's something else. In reality, it's the underlying power spectrum, what our theoretical model predicts, but it's convolved with something else. And this something else is basically the signal from the non-uniform distribution of galaxies. So there's no way of getting rid of this in Fourier space. In configuration space, when we're measuring the correlation function, actually we are measuring this excess of power of our data catalog with respect to another data catalog, which is the random catalog. And it's very easy because we just have to take the ratio among them. But in Fourier space, we are taking the Fourier transform of this F2 field. So actually, everything gets imprinted there, and there is no easy way of taking out of it our signal. So what we do? What we have to do is instead of taking out from our data signal, putting in our model signal. And this is this can be done in several ways, but probably the most elegant way and simplest way it's described in this recent paper, which is basically writing out the power spectrum multiples as not as a Fourier transform of the correlation function, but something similar, which is called Hankel transform, which instead of have this kernel, which is not exactly an exponential, but is a spherical Bessel function. So just a simple way, this would be like our theoretically predicted power spectrum convolved with the window, and this is related to our theoretical correlation function, which is convolved with the window, and this is how the convolution works. So actually, these guys here, which is the same guys that we put here for the monopole and for the quadrupole, it can be written as a function of correlation functions, which are based here, which are without any effect of the mass. And what is here written as a W's is the effect of the window. And this is nothing else but counting the pairs from the random catalog, which contains the information of the window function. So in the ideal case where there is no selection function, so in principle, if our random catalog is totally uniform, these different functions will be 1 and 0, 0. So we will end up recovering that this psi hat would be equal to psi, and psi hat would be equal to this. So, but for real surveys, this is not exactly this. So this is slightly different. And how this looks like is described in this plot. So I'm just plotting here these W functions as a function of distances, their argument. Actually, this plot is just a magnification of this plot. So you see that for W0, it's almost 1 at small scales, and for the other W's, it's basically 0. So actually, this means that for this specific survey geometry, well, things doesn't look that bad, right? I mean, this is almost 1 here, and it starts deviating when we are looking at large scales. And this makes sort of sense, right? For instance, this is the actual survey geometry this plot corresponds. So this is actually Bosnier 14. This is the footprint. So this is right extension as a function of declination. And we see here, for instance, this is the north galactic curve and this is the south galactic curve. And this is what these lines correspond to. So the solid blue lines correspond to the north and the dashed lines correspond to the south. So you see that because these distributions of functions are different, the selection functions are as well different. And at small scales, we see that these functions are almost one, which means that when we are looking to very small scales, the selection function is not very effective. And it makes sense because, I mean, if we're thinking that this is as two pairs of a separate distance, and this distance is small, and we start throwing these sticks that we were talking about, actually, the sticks almost don't see this weird geometry. But if we start making the sticks larger and larger, which is like going to scales larger and larger here, I mean, these sticks are going to be affected by how the geometry is. And now, this means that the window effect is going to start taking it. So how the window function really affects to the measure of the monopole is described here. So this is the blue things are the monopole and the quadrupole, and the solid lines are the original signal. So and the dashed lines are the sort of observed signal, or the signal when it's convolved with the window function. So again, this is in terms of k-space, which means that these scales here are small scales, and these scales here are large scales. So again, the window function has an impact on the measured power spectrum, basically, effectively at large scales, where it's damping the power. Whereas at small scales, it basically does nothing. So how this affects when we measure, for instance, BAO? So you can identify here in the power spectrum, the BAO is not a single feature, but it has been extends abroad a bunch of signals around typically this k equals 0.1, and if we zoom a little bit into this, we see how the original signal, which has this dump here, because of the effect of the window function, it has been reduced. So actually the window function slightly reduces the significance of the BAO measurement. And this has to be taken into account when we measure the BAO, because even if it's not going to affect the position of the peak, it will affect how the dump is. So which is, perhaps for RSD measurements, this is even more important. I just read it here, the very simple model of RSD function, which is the so-called Kaiser model, where the galaxy power spectrum as a function of k and the line of sight can be written as a function of the linear power spectrum produced, for instance, by class or by CAM. And then there is this correction term here, which is accounted by the galaxy bias here, and the line of sight effect here, where f is the logarithmic growth factor. So if instead of working with k and mu, we work with the monopole and the quadrupole just by taking the average, the angle average of these quantities, then you can see that this can be written in these two ways, where we end up having that the galaxy monopole is just a linear power spectrum times this factor here. And for the quadrupole, it has a different. So basically, we have two observables in this case, and well, in principle, we have several free parameters or parameters of interest we want to estimate. One is f sigma 8, which is basically the amplitude of the linear power spectrum with respect to some fiducial value. We have the bias parameter, and we have f. So we have actually, usually this part here is taken as a fiducial, and all the three variables actually can be combined into these two sets of things. So this is what we actually are going to measure from these two equations. So actually, plot just to show how this works is that we have our linear model here that in principle it can have like a free parameter of sigma, which is going to control just the amplitude. And we are going to measure our monopole from the galaxies and our quadrupole from the galaxies. And the difference between at that scale, the difference between our measured linear signal and our theoretical signal and the measured monopole is just going to be this one. And because we also have a freedom in terms of which is the amplitude of sigma 8, actually what we are going to constrain by measuring this difference is this times this, and same for the quadrupole. So again, if we don't take into account for this window effect, with the selection effect, this is going to be very important, right? Because instead of comparing our model to the original signal, we're going to compare to the observed signal. We are not taking this into account. We're going to measure this thing actually less than what it should actually be. So, yeah, these things are important. And in reality, this is just the Kaiser model, so it's a very simplified model. In reality, things are more complicated. You have correction terms that are going to take into account for the nonlinearities that you was describing in the talk before. So this was my first part of the talk. I was describing on the power spectrum, and now I'm going to move to the next observable, which is the bispectrum, right? So what is the bispectrum, and which is the concept of it? So you can, if you think that the power spectrum is the probability of finding 2 points separated by a certain distance, the bispectrum, or the 3-point correlation function, is nothing less but taking into account three areas, right? So you select three sticks instead of just one stick, and then you throw them randomly in your galaxy distribution, and then you compute the excess probability of finding them with respect to a random catalog. And what you find is so the probability of finding objects separated by these R, S, and T distances, nothing else but this thing, where you have like the 2-point correlation functions of each of these sticks, and this excess here would be like the 3-point correlation function, and the Fourier, or the double Fourier transform of these two guys here is going to be called the bispectrum. You can, this is like the formal definition, but actually when you measure it from galaxies, you start from your delta field, and what you do is this. So you impose like these three sticks that have to form a closed triangle, which is imposed like by the Dirac delta here and the correlation function. So in principle, this quantity, it should be 0 if you have initial Gaussian conditions, and this is true at first order. So if your distribution of objects is what is called Gaussian, you will have a 0 bispectrum, right? So you would expect that because our universe doesn't have almost non-primordial non-Gaussianities that was told by Planck, you would observe, if you measure the bispectrum from the galaxies, you would see that it's 0. But this is not true. Actually, if you measure the bispectrum from galaxies, this is significantly different than 0. So you may say that, oh, that's because we have some primordial non-Gaussian signal. And actually, this is not true. What is happening is that nonlinear gravity, the evolution of nonlinearities of the modes caused by gravity is inducing a non-Gaussian signal. So this can be seen easily from perturbation theory that Marín was talking yesterday. So you can write your non-linear dark matter field as a linear dark matter field plus corrections, and these corrections were given by this function with this kernel and these linear delta fields here. And this kernel is the non-symmetric kernel that can be computed from recursive relations. So for the 2-point function, you would just plug in these two guys here, and you just have to do the maths, and then you can see that if you write each of these guys as a sum of these things here, then you can split your brackets into these sub-brackets, where you have like a linear term here, which is nothing else but the linear power spectrum. Then you will have the next order, you will have something which is correlating the linear field with the first non-linear field, that it would be equivalent to do like a 3-order linear field that as Marín was saying yesterday, is a primordial non-Gaussian term, that if you assume that your primordial non-Gaussianities are 0, this would vanish, and the next order is like this one loop terms that Marín was mentioning before, that is P22 and P13. So you can do the same for the bispectrum. And what you see here is that, again, you will have like a primordial non-Gaussian belt. That was the term that you would think that it would dominate, but it doesn't because it's actually 0, or it's very close to 0. So actually the first non-living term, the first non-null term, which is what is called the tree-level term, is actually the coupling between this linear, first non-linear, which is actually delta to the fourth. So this is non-zero because delta to the fourth is it's actually something else. So you can compute this, and you will see that even for a field without primordial non-Gaussianity, you will have it here. And actually, there are more terms here, which is the one rule that would be proportional to delta to the six. So before going into details, perhaps it would be interesting to look at how the bispectrum looks like and how we can plot it. So for just for starting, for the power spectrum, everything it's very simple, because even if we start from a power spectrum which has two arguments, because it's anisotropic, we can just rewrite even in terms of wedges that it would be equivalent to being mu in several meanings, or just to rewrite the anisotropic signal as a different multiple orders. And each of these multiple orders, they only have one argument. So it's easy just to plot P of k for the monopole as a function of its argument, which would be this guy here, or the quadrupole, which would be this here, right? For the bispectrum, things are more complicated because we have in principle 3 arguments here. So one way of plotting it is just fixing k1 and k2 to a specific values and plotting as a function of k3. And this is an option. For instance, in these 3 plots, k1 and k2 has been fixed to be the same, and these 3 plots are showing different beams for k1, and what this plot here is as a function of k3. So actually, what is represented here is actually the Bose DR11 bispectrum from different colors are from the north and from the south galactic caps as a function of k3, and actually k3, so for instance if k1 is equal to k2 as I was saying, and k3 is very small, these signals here will be representing triangles of this shape, and as we move towards k3 larger, then we will be elongating k3 until we reach these triangles around here. So what we see here is that the shape of the bispectrum is changing, is because the triangles which are represented for each different points are changing. So the same thing can be done if, for instance, instead of k1 is equal to k2, we say that k2 is equals 2 times k1, and then different set of triangles are going to be represented as we change the value of k3. So this also, I mean, this way of plotting this is very limited because if we want to plot the whole bispectrum, we have to make a lot of plots, right? I mean, for each beam and each relation between k1 and k2, we will have to make a plot, and we end up having a lot of plots. So another way of looking at it is to think what happens, for instance, for the equilateral bispectrum. So a equilateral bispectrum is a bispectrum with all these k1, k2, and k3 equal 1, and then we just have an argument, and then we can plot the bispectrum just as a power spectrum as a function of one argument. So following this idea, as we can express actually the bispectrum case, we can just set this thing. So we call the smallest k k1, the second smallest k k2, and the largest k k3 without losing any generality, just by definition. So if we impose this condition, whatever triangle we plot here, k3 can go from almost the sum of k1 plus k2 towards the minimum value, the minimum value which would be imposed by this condition and would be just k2. And then we can start ordered triangles. So for instance, we start by the lowest value of k1 we want to take, the lowest value of k2 we want to take, and then k3, it has to have the lowest value because we have imposed that it has to be at least higher than k1. So we start, for instance, by this equilateral triangle, and then we consider as well the next triangle would be like increasing k3 to the higher order, and then we move k1 to the next one, we set k3, we move k3 to the maximum, again. So we end up like ordering all the triangles by moving K1 from the lowest to the next until we reach like a maximum of K. So how this looks like, I mean, we have this plot of equilateral triangles as a function of K1, and instead of K1, we just plot it as a function of this index. We will have something like this. Now our variable is what is called triangle index, and you see that for here, the points are ordered in the same way, which is making spaces between points. And on the top of that, if we plot what is called the isosceles triangles, we will see that all these isosceles triangles are fitting between these points, where all these blue points will have the K1 value the same as this equilateral guy here, but with different values of K2 and K3, and so on. So on the top of the isosceles, we also can include the escalens, and then we end up having like all the triangles ordered by this triangle index. So we are in this way we can represent the whole information of the bispectrum in the same plot. The drawback is that this triangle index is difficult to interpret as a variable because it's just like this ordering here. So we know that, for instance, for K1 values, yes, as index grows, K1 grows, but for K2 and K3, it's not the case because I mean it grows, but it's not growing in the same way. So at the end, yeah, this K3 here can take values of small scales and is not ordered anyway. So coming back, now we know how to plot the bispectrum. Going back to the initial thing of how we represent the bispectrum of dark matter. So from Gaussian initial conditions, we had our non-Gaussian term to be 0. So the first term we had is this tree-level term here that actually, if you work out the math, you will see that it can be expressed this way. So the bispectrum tree level is expressed as the powers of the linear power spectrum of these two guys, of K1 and K2, and then this kernel here. Plus this cyclical means that it's changing, for instance, now K2 by K3, and then K1 by K3. So you will have 1, 2 here, 1, 3 here, and then 2, 3 there. So these kernels actually are derived from perturbation theory and are derived under an Einstein de Sitter universe, because perturbation theory is always assuming this thing. However, it has been tested that the dependence on cosmology of these kernels here is not very sensitive. So even if we change the cosmology from an Einstein de Sitter to a lambda universe, these kernels are not going to change, basically. However, what it does affect these kernels is the theory of gravity. So if GR is not the theory of gravity of the nature, these kernels would significantly change. And this would affect the bispectrum. Actually, it would affect the leading term order in the bispectrum. So this is why it says that bispectrum is sensitive to GR. And actually, we can see it here. So for instance, this is not exactly the bispectrum, but this is something called Q, which is the reduced bispectrum. There's nothing else but the bispectrum signal divided by these combinations of our spectra. And so we can almost not see here this dashed line here, but it's creating this, what is called characteristic U-shape. And it is nothing else but describing how the reduced bispectrum signal changes as a function of the triangle. So we have, in these guys, we have been describing the signal of these triangles, and as we change this guy here, which is nothing else but K3, we are changing from large values of K3 towards smaller values of K3 when the configuration is K2 equals to K1. Yeah. So actually, this U-shape here is going to be dependent on the theory of gravity, and if the theory of gravity is not GR, this shape is going to change. So this is the way we can test gravity using bispectrum measurements. Of course, this is the ideal case of dark matter. In reality, we have galaxies, so our bispectrum is affected by bias. We have rate-space distortion, so this is also going to affect our measurements, and things are going to be getting a little bit more complicated. So for instance, if you want to take into account the galaxy signal, you can just pick out your favorite galaxy model. For instance, this one that has been described in the talks before, where it has like a starting linear bias correction, then plus a non-linear bias, and plus something else, which is called the non-local linear bias. And then you can do perturbation theory in the same way you did before. So for these non-linear delta fields, you just plug in your expansion perturbation theory in each of these ones, and then you start computing brackets between galaxies, delta galaxy, delta galaxy, delta galaxy, and then you will see what it comes out. And I just have written it here, so that the first order bispectrum for galaxies with a bias, it can be written in this way. So we have this F2 term here. So basically, if you set B1 to 1 and B2 to 0, then this guy vanishes here, and then you recover the expression I was written before. But if you consider the bias, then there is this term coming here, and you can see that the way the bias enters into this signal, it depends on the shape. So for instance, this B2 here enters as nothing else but a constant term. B1 enters in different terms here, where F2 is the kernel I was written before. S2 is a different kernel, which is slightly different as F1. So basically, the way the signal of the bispectrum is going to change as a function of the angle between these two guys here is going to be different for each guy's parameter. So this is basically allowing us to measure these bias parameters if we can measure the different bispectrums. And this is what I did, for instance, here. I think this is an interesting plot. This is B1 and this is B2. Each of these points is coming from the estimation of B1 and B2 by measuring either the power spectrum or the bispectrum, or a combination of both, of 650 halos. So for instance, if you start looking at the blue points, it is measuring just using the power spectrum. And you have this shape here. So you see that the power spectrum is very good at measuring B1, which is sort of expected, because the first order correction of the galaxy power spectrum is just B1 squared times the linear, right? However, it's very bad at measuring B2. You see that this spread thing here, B2 is not clear, it can go from 5 to -2. So basically, it's telling us that the error bars of each of these measurements is super big. This shape is actually, it's sort of an MCMC thing. It's sort of tracing the likelihood contours of our parameter. If you use the bispectrum alone, you see that B1 is not very well measured, and B2 neither, right? Not really. I mean, a little bit better, but not really. However, what it constrains is a line between B1 and B2, which is very interesting, because when we combine the power spectrum and the bispectrum, we get like the crossing of these two guys here, and then we have a good measurement of B1, but also a good measurement of B2. We can go to redshift space distortions, and things gets even more complicated. So you can do perturbation theory for redshift space distortions, and you end up seeing that the way the bispectrum modeling evolves from real space to redshift space is sort of promoting these F1 and F2 kernels to a new kernels, which are called usually Z, and which are written in this way. So you see that Z1 kernel is nothing else but a Kaiser term, and the second order kernel is this sort of complicated thing, which depends of course the initial F2 parameter, but then it starts depending on the mu, which is the line of sight of one k, of the other k, F parameter here, it appears the velocity kernel G2 here. So it's sort of complicated. And this is just for the leading order term. So it's the first order correction. So the galaxy, the redshift space distortion galaxy bispectrum, I mean, can be simply written in this way, but take into account that these Z kernels are complicated. So if you integrate these without weighting by anything, you will get the monopole bispectrum, and if you start weighting by other things, you will get more complicated things, which I haven't written here, but they takes like the whole thing to be written. And this is just for the first leading order bispectrum. However, I think
a more intuitive way of seeing how this bispectrum constrains parameters is actually plugging all these equations and start constraining parameters from endpoint simulations and see how it looks like. So for instance, in this plot here, this V1 is F, this sigma A, and for the different colors, it's just how the parameters are constrained by using different combinations of observables. So for instance, for blue ones, I'm using the power spectrum monopole and the bispectrum monopole. The green ones, I'm using the power spectrum monopole quadrupole, which is the typical thing, and the red one is a combination of these three. So for instance, for the green points, it's very interesting here in the F sigma A plot that you see that all the points are along a line, which is actually the F sigma A constant line. So this is nothing surprising because we have seen that by measuring the monopole and quadrupole, we can only constrain F sigma A as a constant, but not F and sigma A alone, because these parameters were completely degenerate. However, if we add the bispectrum to the power spectrum monopole, we see that actually the line we constrain is different from the line of F sigma A equals constant, is these blue guys. So by plugging on all these three parameters, we actually can break the degeneracy between F sigma A. I mean, it's still an elongated line here, but it's not as square as it was initially for the power spectrum monopole and quadrupole. Another way of seeing this is actually by taking your model and making a simple exercise. You just take F to be equal to V1, for instance, and to be equal to F sigma A to minus 1. Right? So this is basically setting F sigma A to a constant value, whatever it is, just 1 for reference. And then start changing X. So if you start changing X, you don't touch F sigma A, but you touch the individual parameters. So this is for the power spectrum monopole, quadrupole, and the bispectrum. So as a function of scale. So at large scale, basically, it's Kaiser model, and touching this thing is not doing anything. It's not changing. Why? Because the first order approximation model for the power spectrum is insensitive to the independent values of F and sigma A. It's just care about the multiplication of them, and this is set to 1 by definition. So it's not changing anything. So we cannot measure F and sigma A independently. This is why we were getting this line here. However, for the bispectrum, you see that even at large scales, the bispectrum is sensitive to the values we put here, F and sigma A, even if the product is set to 1. So you see here that F and sigma A is changing, and the bispectrum is zero. So this is why we could actually measure something around here. And this is actually what we did in this paper for sigma sample for the both galaxies. So we could put constraint of F and sigma A parameters independently. Just in the last minute, I'm just going to talk about another interesting property of the bispectrum. So Will was mentioning about the reconstruction technique that was applied to the power spectrum. So actually, by doing reconstruction, we are sort of not only linearizing the galaxy field, but also Gaussianizing it. So actually, if you measure the bispectrum in the post-reconstructed field, you will see that this bispectrum is way smaller than the actual bispectrum from the pre-reconstruction field. So when you measure the BAO signal in the post-reconstructed field, the pre-reconstruction effect, what it has done is pull back information that it was in the bispectrum back to the power spectrum. So actually, an alternative way of improving the measurements of BAO without doing reconstruction, and therefore without assuming a theory of gravity, is measuring not only the power spectrum, but as well the bispectrum in the pre-reconstructed field. And by doing this, we can extract, in principle, as much as information from measuring the power spectrum in the post-reconstructed field. So just as final conclusions of the bispectrum part. So remember, bispectrum is essentially a nonlinear quantity. Even at first order, it contains delta 2 terms. It's sensitive to GR, and this is the main motivation of using bispectrum to measure things. If we want to test the theory of gravity, it's probably the best observable to look at. But also, it's very good to measure the second-order bias time. We've seen here that the second-order bias time was poorly constrained by the power spectrum alone. And finally, it also can be used to measure F and sigma 8 independently, which is something which is not, we cannot do it using the power spectrum alone. And that's it, thank you.